Okay, 1.4, working with radicals. What we need to do here is look at what a radical is and how to simplify them. So that's what we're working on in this section. Now, the definition of a radical. There are different types of radicals that exist. Something called an entire radical, which is a root sign. You guys know this as a root sign. We're going to call this a radical sign because it could be the cube root, the fourth root. This is known as the radical sign. So an entire radical means that the entire number is inside the sign, underneath the sign. There is no number on the outside. Okay? A mixed radical is something that has a number on the outside and a number on the inside. It is a mix of a whole number and a radical. Now, entire radicals can be simplified to a mixed radical, and we're going to look at examples of this. Example number 1. You're asked to simplify each. So the square root of 50. How would you simplify the square root of 50? Well, when you simplify the square root of 50, you need to look for a perfect square that is found inside the number 50. So, inside the number 50, you know that 25 times 2 is equal to 50, and one of these numbers, the 25, is known as a perfect square. Why do we want this? Well, what is the square root of 25? And the answer to that is 5 root 2. 5 root 2 is the mixed radical of the entire radical square root of 50. 5 root 2 is the simplified form of root 50. Root 98, root 72, and root 63. Let's look for numbers here. Root 98 is equal to this. Now, before we do any of these, let's go over the rules. First rule is to find a perfect square factor, a number that can be divided out of the number inside the root that is a perfect square. What perfect squares do you need to know? Well, you need to know from 1 squared to 30 squared. So let's go over all of those. What are all the perfect squares from 1 squared to 30 squared? 1 squared is 1. So we will have 1, 4. Okay, let's go. Sorry, we're going to list them all here. 1, 4, 9. 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. 5 squared is 25. 6 squared is 36. 7 squared is 49. 8 squared is 64. 9 squared is 81. 10 squared is 100. And then 11 squared is 121. 12 squared is 144. 13 squared is 169. 14 squared is 196. 15 squared is 225. 16 squared is 256. 16 squared. 17 squared is 289. 18 squared is 324. 19 squared is 361. And 20 squared is 400. We're still not done yet. We need to go to 30 squared. Okay, 21 squared is 441. 22 squared is 484. 23 squared is 529. 24 squared is 576. 25 squared is 625. 26 squared is 676. 27 squared is 729. 28 squared is 784. 29 squared is 841. And finally, the last one, 30 squared, is 900. So these are all the perfect squares from 1 squared to 30 squared, all listed there for you. Now let's go back to the question. The reason why we do all of this, folks, is because we want to make sure that we can simplify radicals without the use of a calculator. Why? Because occasionally you're going to come across where a calculator is not available or you don't have the opportunity to use one. So we need to be able to simplify simple radicals and look at the puzzle and solve it. Root 98 is equal to 49 times 2. Root 49 times 2 reduces itself to 7 root 2. Root 72 changes itself to root 36 times 2, which gives you 6 root 2. And finally, root 63 changes itself to root 9 times 7, which gives us an answer of 3 root 7. So you need to be able to simplify a radical from an entire radical to a mixed radical. Example number 2 asks us to convert each of the following to an entire radical. So what you're given is a mixed radical and you need to convert it backwards. Well, to bring 7 back inside the root, it becomes root 49 times 3. And that gives us an answer of root 147. 12 root 2, when the 12 comes back inside the root, becomes root 144 times 2, which turns into root 288. Finally, the last one, 10, moves inside the bracket to become root 100 times 5, which is an answer of 500. All right, moving forwards. Like radicals can be combined through addition and subtraction. An example is 8 root 6 plus 2 root 6 minus 4 root 6. Why does that equal 6 root 6? Well, you have 8 root 6's plus 2 root 6's. That gives us a total of 10 root 6's. And then we subtract 4 root 6, and that gives us a total of 6 root 6. So the idea is you treat the root 6 as a common like term. And we combine all the like terms together. So the root 6 could be treated like a radical. Like a variable. You need to collect like variables. So again, the same root is the only time that you can combine like radicals. They have to be the same root. Now radicals can be multiplied using the distributive property. And how we do that, let's look at some examples. 4 root 3, for example, times a set of brackets or a multiple set of brackets as such. When we expand this, we take the 4 root 3 and we distribute it to each piece on the inside. So 4 root 3 is going to be multiplied to 3 root 2, and that gives us 12 root 6. And 4 root 3 gets multiplied to negative 3, and that gives us negative 12 root 3. So how, when you multiply radicals, what are you actually doing is you're taking outside numbers together and multiplying them, and inside numbers together and multiplying those. If they need to be further reduced, that's when you'll do that. All right, the next example, root 3. So you treat this exactly like FOIL, and we're going to expand this out. So root 3 times root 3 is root 9. Plus 4 root 3 minus 2 root 3 minus 8. Okay, before we go into and explain all this, let's go slowly and explain where each one of these 4 terms came from. Root 3 times root 3 gave us root 9. Root 3 times plus 4 gave us plus 4 root 3. Minus 2 times root 3 gave us minus 2 root 3. And finally, minus 2 times 4 gave us minus 8. So that's how we expanded it. The next step is to collect any like terms and simplify any radicals. Note, I hope you see that root 9 actually simplifies itself to 3. So technically, you could have replaced this root 9 automatically with a 3. So we could have replaced that plus that root 9 with a 3 right in the beginning. And if we had done that, we could have then collected the like terms. Ultimately, the answer here would still have been not 11 plus 2 root 3, folks. Sorry about that. It will actually turn into minus 5 plus 2 root 3. So the answer turns into minus 5 plus 2 root 3 as our final answer. All right, moving forwards. Example number 3. Simplify the following. So you've got a bunch of radicals going on here, and you're asked to simplify them. The way they look right now, there's no way we can collect like radicals. But remember that radicals must be reduced first. So we're going to reduce all of these to a more simpler entire mixed radical. So, first step is to simplify each individual radical. So 5 root 12 will change itself into 5 root 4 times 3. 3 root 48 will change itself into 3 root 16 times 3. Because 48, some of you might have thought, oh, 4 goes into here. Yes, it does, but it is not the largest possible perfect square. The largest possible perfect square factor is actually 16. And root 27 breaks itself up into 9 times 3. Why did I put those numbers in the front? Remember that these are our perfect squares. So the result will be 10 root 3 plus 12 root 3 minus 15 root 3. Why? Because the 4 comes out and that becomes a 2. 2 times 5 is 10. The 16 comes out, it becomes a 4. 4 times 3 is 12. The 9 comes out, square root of 9 is 3. 3 times 5 is 15. So this is what we end up with. Now we look for like radicals, which we have. And fortunately for us, the answer to this is 7 root 3. So one more time, we collect like radicals to get this answer. Let's try another example. What does this mean? Well, some of you might be trying to put these two together. You can't. The reason why? BEDMAS rules always apply. And they say you must multiply these out first before you can combine it. Before we do any of that though, we want to simplify. Root 8 is root 4 times 2. Root 32 is root 16 times 2. And then inside the bracket, those were already simplified. So we have 2 root 2 plus 4 root 2 times what's inside the bracket. Now some of you might be going, oh, I can put those two together. Wrong. The reason why is because this has to multiply to the bracket first. It's like there's a reason there's a bracket here. That bracket is attached by multiplication. BEDMAS rules say that multiplication must happen first before we can combine this number. So we have 2 root 2 minus 8 root 6 plus 8 root 2. Now, folks, we can look at this question and say, okay, these are all simplified radicals, and now we can collect any like radicals. And this is just explaining here that how each of these got multiplied to give you this whole line right here. This whole line is done by multiplying the minus 4 root 2 out. And we get an answer of 10 root 2 minus 8 root 6. That is our final answer. All right. Part C, one more question, or a couple more questions here, folks. Let's look at these. You need to expand that. How do you expand this? Well, you see the square. That means there's double of these set of brackets. So we write it out with double the set of brackets. Now, expand that as such. So you get 25 minus 10 root 2 minus 10 root 2 plus 4 root 4. What is 4 root 4? Square root of 4 is 2. 2 times 4 is 8. So you could have actually made this a 2 right away if you chose to. You will end up with, see, we're changing it to a 8. The reason why it turned into an 8 is 4 times 2 is 8. So you can do that. You end up with, once you collect the like radicals, 33 minus 20 root 2. Next one. 2 root 3 times 2 root 3 is 4 root 9. 4 root 9, folks, is 4 times 3, which turns into 12. 12 plus 10 root 3 minus 10 root 3 plus, minus 25. Collect the like terms and you get minus 13. Why? Because these two cancel each other out and there's nothing left. So we do not write anything when we have 0 of something. This will be important in the future. So this idea that a radical can turn itself into an integer will be important later on in the future. We will be doing this, okay? Look at the top, look at the answer. Interesting how radicals, normally when we expand it, have radicals, but in this case, it turned into a special type of number. In fact, it turned into an integer with no radicals. This is going to be important in the future. All right, folks, that's the end of the lesson for today. Have a numerical day. Take care.